Welcome back to our series on applied regression analysis. I'm Mark Ledbetter, and this is lecture video 40, and we are going to discuss the code for chapter 14, Diagnostics, in terms of a multiple regression model. So let's get started. Again, this is an RMD or R Markdown document, and this is required, this document, specifically this one, is required for you to use for your homework for chapter 14 and for your project number 2. And what you will do is modify this code, and then you will add code from chapter 8 and chapter 9, that file, but it needs to be this code, start with this and modify from here. All right, so that is a requirement for this class. Okay, so let's run this first chunk by clicking there. As you see, it minimized my console. I'm going to undo that. And if you run into an error with running these library statements, then make sure that you uncomment the appropriate install.package here, because OLSRR. So I've put that in there for you now so that you can install the package. Once you've installed it once, you don't have to do it again. I'm going to use Control, then Shift, and then C, holding those keys down. That comments all of those, and then reversing that would be Control, then hold Shift, then hold C, and it puts it back. So we're going to use this OLSRR, which stands for Ordinary Least Squares Regression something. I don't remember, but it's going to be very important here. Okay, so we have our data. Now, in this data, we have the first column is child, and that's just the number, 1 through 12. This is important to note because it's going to require us to be careful and not to analyze this just ID number, if you will, that's not meaningful. So just 1 through 12. We do need it in there, basically for the order. I'm going to plot the observation number, I could call this, in some cases. So this is going to show us, we're going to say time, but we'll discuss that when we get there. And then down here is where I add the age squared to this data frame. All right, and so that's the code we have before. Remember that in order to get credit for your work, you have to have the data inside the code so that I can run your code when I grade it. Otherwise, if I can't run your code, then I can't give you credit for your work because I can't run your code to verify it. All right, so we're going to set our alpha, our significance level, to 0.05. Please notice that I did not just use the word alpha, as it may be a keyword in some package somewhere, so I've used alpha 1. This is always a good practice not to use something that could be a keyword. We're going to, and we're using this data set that we've seen before with the weight, height, age, and age square of malnourished children. All right, and this was chapter 5, problem 2. Okay, so one of the things that if you have run something before and you want to get rid of everything, there's this clear all output here from the gear, and we'll do that just to make sure that I run this stuff again. All right, so this is my model. It's the full model, all the variables in there. And so height, age, and age squared. Now I want to show you that there is an easier way to write the full model if we didn't have that variable child in there. If we were going to use all of the variables besides weight as predictor variables, then we could do this. We could write WGT and then the tilde, and then we could put a period, and then data equals df1. All right. The problem with our data set is that we have this variable child in there, and we don't want to analyze it because it's just a number from 1 to 12, so it's certainly not going to be predictive, we hope, of the output. All right. But if you had a lot of variables in your data set and you were going to use all of them in your model, And of course, you would put your y variable here, and then you're going to use all the other ones to predict it. Then you could just put this period. And that's a much shorter and easier way to do this rather than writing out all of the variable names with plus signs in between them, which is not too bad with 3, but when you have 20 or 30, it becomes a little more difficult. Now, I also have the null model in here, but we're not going to use it in this video. So I'm going to run this, and now I have my model. Now, the OLSRR data package, or the Broom, one of the two, has this nice model diagnostic metrics package, and so it has this function augment, and it takes and augments our model that we want and makes it a table, which is really nice. It gives us a lot of things. So I can do that and show you what this looks like to start with. And so we have our variables, and we have the predicted values or fitted, SE fit, so the standard error of the fit, residuals, hat, the hat leverages, sigma, Cook's D. We have standardized residuals, lots of things, but not everything that we want. I would like to have the Cov ratio, the covariance ratio, and the Jackknife residuals, or studentized residuals. So I'm going to add this to the full, but I really didn't end up using that after all. So I'm adding the Cov ratio here, and I'm adding the studentized residual here using these functions. All right. Cov ratio and stud res. So now I create this now, but adding that to the LM full does not mean that it gets passed to the model diagnostic metrics table here when I use augment. It ignores those. So I have to add them separately to this table. So I'm going to do that using stud res and Cov ratio again. And then when I print this out, I now have everything I had before, but also the studentized residuals and that covariance ratio. Okay, so the first thing we're going to do is look at the residual plots. And the very first plot is the plot of the Jackknife or studentized residuals against, and this is versus predicted values. And so with this, we can assess any issues with linearity, homoscedasticity, and independence. And so let's go ahead and run that. Now, originally, I had written a function with the plot function, but I found in OLS that they had a much nicer plot here than mine. And they even give us this threshold, the absolute value of 2, and it shows us that a potential outlier is observation number 7. So that's very nice. But that's not what we're looking for right now. Right now, even though observation, I said 9, it's 7, appears to be far away from the rest of the data, what we're looking for are violations of homoscedasticity, or the homogeneity of variance, or the linearity. So we don't see a change in linearity across here, some pattern like, it doesn't dip down like a parabola, or dip up or curve up like a parabola, or log or square root or anything else. So it's pretty much and when you plot this line at 0 and look at it, you see that it just varies around there. But observation 7 is far away from 0 and the rest of the data. And then we have this observation here that is kind of a borderline outlier. It's not, but it's kind of close to that, right? Okay, so that's the first plot that we look at. And we have identified a potential outlier, but that really wasn't the purpose of looking at this chart right now. It was to evaluate homoscedasticity and linearity. Now, I need to change this. Yeah, that was 7. Okay. So now we're going to look at the Jackknife against time. And in this case, I don't really have a time period, but I'm going to use the order of the observations. That's usually how we measure time. They're usually put in order of the time that they were taken, right? So let's take a look at that. And again, I see about the same picture. I don't see very much difference. It's not like I see this increasing over time or decreasing over time. I don't see a violation of independence, or there does not appear to be a dependence or pattern across time. So we've met that requirement that we have independence. We don't see a violation of it. Let's put it that way. Now, in the charts that follow, the three most extreme values will have numbers beside them. Okay. So we're going to look at residuals versus fitted. And this is used to check, again, the linear relationship assumptions. We should have a straight line at 0, and the residual should be approximately symmetric about that line for all the fitted values, and that would be the best case. Now, practically, we should not see an obvious pattern. There should not be there should be an approximately equal spread across the fitted values, but sometimes this is difficult to see when we have a small sample size. Okay, so let's look at this plot, and it's going to look very similar to what we've seen before, and we see that 7 and 4 and 5 are our three most extreme values. 7 does appear to be unusual or a potential outlier. Okay. Now we're going to look at scale location, or the spread location. Is again used to check homogeneity of variance of the residuals or homoscedasticity, and there should be no evidence of funneling or a change in the variation. And when we look at this, we see that the variation is fairly consistent. We might see that it appears that it may be increasing around here, but again, with the small number, it's very hard to tell. There's just not a lot of values over here on these smaller fitted. For the smaller fitted values, there aren't a lot of points. So we have a very hard time saying that there's a change in the variation across the fitted values. So it looks fairly consistent, so I would say that this is fine. Again, this is a very difficult thing to see, but if you see an obvious pattern where it just obviously got bigger or got smaller as far as the variance, the spread changed, went from small to large, then that would be an issue. Now the next thing we're going to look at is a normal QQ plot. And so this is the theoretical quantiles with the fitted values, okay? And these are the standardized residuals. And when we look at these, this is a pretty nice fit to this normal line, the dotted line in there. The only value that's really, and again, the three most extreme are 4, 5, and 7. The only one that's far away from the line is 7, but that's in the tail, and we expect that that will happen from time to time. So this is not a violation of normality. I would say that this model meets the approximate normality assumption. Right? Now we're going to test for the violations. Really, I shouldn't say of the model. I should say not violations. I should say these are tests for outliers and extreme or influential values. Now, the first thing we're going to look at are the hat leverages. All right. Now, I want to remind you that the hat leverage, it's the distance of each point from the mean or the center. And so let's say, for example, a data set that contains k predictor variables, x1, x2 to xk. The geometric distance from the ith predictor point, which would be given by xi1, xi2 up to xik, that distance to the center or the mean, which would be that bar is a little off. Oh, that's why, because I don't have it in the right spot. Okay, that didn't look right. All right, we want that here. Okay, so x bar I1, x bar I2, x bar Ik, that would be the center point. And so the hat leverage is that geometric distance from the center there, the bars, to the ith point, okay? And so the rule of thumb that we use is that we, if the value of that distance is more than 2 times k plus 1 over n, then we consider it as a potential outlier. okay? And K is the number of predictor variables, and N is the number of observations. And when we look at this, and I had to write this code, so I didn't find it anywhere that we could look at this and do the comparison. So what I did was it's going to give me observation 9 and observation 11, and that's because these hat values are above this maximum hat value that we should see, which is 2/3. So I used the equation here, 2 times k plus 1 over n, and that turned out to be 2/3, and these two hat values are slightly above that. So these would be potential outliers, observations 9 and 11. Now I did the same thing with the Jackknife or student residuals, okay? And we compare this to a t-statistic, and particularly the t-statistic with n minus k minus 2 degrees of freedom, and that's supposed to be 1 minus alpha over 2 as the potential outliers. There's a more conservative value, which would be the Bonferroni, where we take and we say 1 minus alpha over 2 times n. And so let's run this. And again, I had to write this code, and I've got a little duplication here, but I couldn't quite figure out how to get rid of it without taking a lot of time, so I left it for now. And so we might have to get rid of something when we well, we'll just have a little duplicate there when we print it out, but that'll be okay. If I figure out how to get rid of the duplication, I'll let you know. But I had to use this function print, and when you use the function print, even though you assign it to something, it still prints it out, even though I didn't want it to. But when I didn't use that, I didn't get a very good, I didn't get a data frame or a matrix like I wanted. So we'll have to look at that when I have more time. Okay, so here I have set up and looked for that value of t, that cutoff value for n minus k minus 2. And then here I've looked at, so I changed alpha. So I changed this to from 1 minus alpha over 2 to 1 minus alpha over 2 times n. Okay, and that's the Bonferroni. And so we run this and we see that observation 7 keeps popping up. Its studentized residual or jackknife is above the 2.36, let's say, max value, but it's not above the maximum jackknife Bonferroni cutoff point. Okay. Now, let's move on to Cov ratio or covariance ratio, and it measures the change. Oh, and I didn't talk about what this is. So what a studentized or jackknife residual is, the standardized residual, it's divided by its standard deviation. And the jackknife is where you remove the current observation and calculate the residual based on removing one observation at a time. Okay. Now the covariance ratio measures the change in the covariance matrix, and we talk about fixed effects. That would be more important when we're talking about the design of experiments, but here we're doing regression, so we won't get into that. So it's the change in this covariance matrix when we delete a subset of observations. And in this case, we're doing the current observation. So the covariance ratio compares the ratio of the determinants of the covariance matrix. Or I should say matrices. Okay. And the rule of thumb is that the values should be in the range of 1 plus or minus 3 times k plus 1 over n. And so let's look at this code that I wrote. And again, I have a duplication, which I need to get rid of. And in this case, it looks like most of them exceed the maximum value. And the minimum would be 0, and there can't be less than 0. The max would be 2, calculated this way. And I have a lot of them. In fact, I have 3, 6, 8 of the 12 are above this. So this covariance ratio seems to be a pretty sensitive ratio because none of the other tests give me this type of result. Okay, so now let's look at DF fits. It quantifies the number of standard deviations that the fitted value changes So the predicted or fitted value changes when the ith data point is omitted. And so the general rule of thumb is this should be that if it is greater than 2 times the square root of k plus 1 over n, then that would be a potential outlier, or I shouldn't say outlier, this is a potential influential point, because it changes, it's influential in that it changes the model, okay? So an outlier is something that could change the model, but it's far away from everything. An influential point usually is far away, but it's far away near the tail, okay? So, and we saw that value 7 was very far away near the tail of the normal plot. So that means that it's going to have more leverage or more ability to change the parameter values in the model. Okay, so a more conservative estimate is that DF fits is greater than 2. The absolute value is greater than 2. So let's take a look. And this threshold was 1.15. This was calculated by OLS, and I didn't check to see if the square root of k plus 1 over, so that would be 4 over 12, 1/3, 2 times the square root of a third. Let's check that real quick. 2 times square root of 1/3, and that is 1.15. So they are using that same cutoff. If we're using the conservative cutoff of 2, we don't have any values that exceed that. But you see that observation 4 and observation 7 here are beyond that threshold, but not terribly far beyond the threshold. Okay, so these are potential outliers unless we use the more conservative measure. Okay. Now, Cook's distance, it's the extent, it measures the extent to which the estimates of the regression coefficients change again when an observation is deleted from the analysis. So it's another way of looking at what happens, like DF fits. It's just another way to calculate this, Cook's distance. And we're saying that the potential influence points are influential points if DI, the Cook's distance, is greater than, for the ith observation, is greater than or equal to 1. And I noticed that the OLSS package, and it's not in Broom, it's the OLS package. Those are two different packages. I thought they were the same, but they aren't. They use a different threshold to calculate the influential points. And so they came up with a third, but in any case, none of the Cook's distances are even that far away. So, and we also have a bar. So there's a bar chart here, that's the first line of code, or there's the chart, the line chart. So I think the line chart's a little bit better because it has the threshold line drawn. So I like that myself. And then we're going to talk about the DF betas, and this is the difference in each parameter estimate with and without the influential point. Now this is the actual change in the, this is not the standard deviation, this is the actual value that the beta changed. And so there are n times k DF betas, okay? So large values of DF betas, they identify observations, again, that are going to be potentially influential points. And so when they're greater than or equal to 2 over the square root of n, they're considered influential points. Let's see what we get. And so we have these, as they mentioned, we have these for each of the k predictors and for each point. So when I look at the intercept, I see that observation 2, 4, 6, 7, yes, I can see there is a 7. I can't zoom in on it for you, unfortunately, but 7 is influential here. And 7 is also influential under age. So this is the intercept, this is age, this is height, and I've got 9, not 7, but this is observation 9. And then under age squared, none of the observations are outside of the threshold. Okay, so 9 and 7 appear to be influential. 7 for the intercept and for age, 9 for height. So now let's look at the standardized residuals. And these are called internally studentized. And again, that means that we're dividing by the standard deviation. And the threshold is usually 2. So anything above 2 is considered a outlier, and we see again 0.7 is beyond that threshold. Okay, so that is how we test for outliers, influential points. We've tested to see if the assumption of normality, homoscedasticity, linearity, we've looked at all of those assumptions now, and sometimes in many different ways. Now we want to talk about something called colinearity. And this exists when there's a strong correlation between the independent variables in the model, so the predictor variables. We want there to be a strong correlation between the response variable, what's being predicted, and the predictor variables, but we don't want there to be a high correlation between the independent predictor variables, because then they're going to produce unreliable and unstable parameter estimates and larger, that's going to inflate the standard errors as well. So we can do this very easily with a correlation matrix. And so notice that I did not include child in here. So I did not include that first column. I've only included 2 through 5. And so we look at this. Let's take a look. Weight is across the top. Obviously, weight and weight is correlated with 1. So we see our diagonal of 1s through here. That's just that we ignore because those are the variable correlated with itself. And so we can either look at the top above the 1s or below the 1s. We don't need to look at both because it's a symmetric matrix, and weight with age here is going to be the same as weight with age here. All right, the order doesn't matter. So I'm interested in height and age first. 0.6. So we're really interested when it's above 0.7 or 0.8, and whether you use 0.7 or 0.8 depends on which area of analysis you are, what your area of expertise is. So if it's psychology, it may be one thing. If it's engineering, it may be another. All right. So I look here and I see age and age squared is 0.994. That's extremely high. I do not want both of those in my model because there's too much correlation between those two. And so now, in order to determine, and it makes sense because age and age squared, obviously, they're the same variable, except age is the square of, age squared is the square of age, right? So it makes sense that they're very highly correlated. Now, when I look at weight, I'm going to get rid of the one that has the smallest correlation to weight, and that would be, although barely, age squared. So age is the one that I would keep in the model because it's more highly correlated with weight. There are other ways to determine this as well. We might look at the model fit instead of using the correlation to determine this. So we could compare the two models and see which one is best as far as a p-value for the, we could do a partial f-test and say, well, which one of these, or variables added last, right? Variables added last, where we look at age square added last and age added last, and whichever one was more significant, we would want to include it rather than the other. Okay. So now, in conclusion, we don't see a violation of homoscedasticity or independence. The normality plot only shows one outlier, and that was in the tail, and we kind of expect that. So this model is actually acceptable for prediction of the weight in undernourished children. However, the one problem we did find was colinearity between age and age squared. So we would remove age squared because its correlation, because of its correlation to weight, because its correlation to weight is slightly smaller than the correlation of age to weight. And again, you might use another measure to do this. Correlation is one way to do it. There's other tests. The f-test might be another way to do it. And then there's other model fits that we haven't talked about yet, and those might be another way that you might decide which one to keep and which one not to keep. Okay? Now, please make sure that you upload your lecture notes to the Google Drive on the date listed on the course calendar before midnight. If you have questions, please come to office hours, virtual office hours. If you can't do that by the time you need the help, by all means email me, but email me a picture of the problem and a picture of your work so I can see your approach to it, and I'll be glad to help you by email as fast as possible. Until next time, stay safe, and we'll see you then.